Carburization corrosion damage mechanisms as a part of high-temperature corrosion greater than 400 degrees Fahrenheit or 204 degrees Celsius. Based on API 571, carbon is absorbed into a material at elevated temperature while in contact with a carbonaceous material or carburizing environment. Certainly. Here's a detailed description of carburization damage, starting with an introduction. Carburization damage is a form of high-temperature material degradation that occurs primarily in ferrous alloys, such as steels and cast irons, when they are exposed to carbon-rich environments at elevated temperatures. This phenomenon results from the diffusion of carbon atoms into the surface layers of the metal, leading to significant alterations in microstructure, mechanical properties, and overall component integrity. Nature of carburization damage. Carburization damage manifests through various microstructural and mechanical changes. Thickening of the carbon-rich surface layer. Excessive carbon infiltration leads to the formation of a hard, brittle case on the material's surface. While a controlled carburized layer can enhance surface hardness, excessive carburization results in a thick, brittle layer prone to cracking. Microstructural changes, formation of cementite, iron carbide, Fe3C, and other carbide phases, depletion of alloying elements like chromium, manganese, or molybdenum from the matrix, weakening corrosion resistance and toughness, grain boundary carbide precipitation, which can cause local embrittlement. Mechanical property deterioration, increased hardness and brittleness at the surface, reducing ductility, reduced toughness and increased susceptibility to cracking, spalling, and fatigue failure, development of microcracks initiated at the carburized layer or along grain boundaries. Residual stresses, thermal gradients and microstructural changes generate internal stresses, further promoting crack initiation and propagation. Here's mechanism of damage formation. The process begins with the diffusion of carbon atoms into the steel's surface during high-temperature exposure in a carbonaceous atmosphere. Over time, the diffusion layer thickens, creating a hardened case. If the process is excessive or uncontrolled, the surface becomes excessively hard and brittle. Microcracks develop, especially under mechanical loads or thermal cycling. Cracks can propagate inward, leading to spalling or complete failure. The microstructure degrades, losing toughness and ductility. Then, the factors influencing carburization damage. Several factors influence the severity and occurrence of carburization damage, including temperature, exposure time, atmosphere composition, material microstructure, and component geometry, as previously detailed. Impacts of carburization damage. The consequences of carburization damage are often severe. Number 1 is component failure. Cracks and spalling weaken structural integrity, leading to premature failure. Number 2 is reduced service life. The formation of brittle layers shortens the lifespan of components exposed to carburizing environments. Number 3 is operational difficulties. Damage may cause malfunctions or unsafe operating conditions, especially in critical applications like turbines, heat exchangers, and pressure vessels. And number 4 is increased maintenance and costs. Repair, replacement, and downtime are increased due to damage. In summary, carburization damage is a critical concern in high-temperature applications involving ferrous alloys. It results from unwanted carbon diffusion that alters the microstructure, embrittles the surface, and leads to crack initiation and propagation. Understanding the mechanisms and influencing factors is essential for designing processes and selecting materials to prevent or control carburization, thereby ensuring the durability and safety of high-temperature components. Carburization damage affected materials based on API 571, carbon steel and low alloy steels, 300 series SS and 400 series SS, cast stainless steels, nickel base alloys with significant iron content, e.g., alloys 600 and 800, and HK/HP alloys. Certainly. Here's a detailed explanation of the materials affected by carburization damage, focusing on their composition, microstructure, and how they are impacted. Materials affected by carburization damage. Carburization primarily affects ferrous alloys, materials that are based on iron, due to their high affinity for carbon at elevated temperatures. The main categories of affected materials include various steels, cast irons, and some high-temperature alloys. Here's a comprehensive breakdown. Number 1 is carbon steels. includes, number of carbon steels is plain carbon steels, comprise iron with a carbon content typically ranging from 0.05% to 2%, at elevated temperatures, carbon diffuses into the surface, forming a hardened case. Damage manifestations, includes, excessive surface hardening leading to brittleness. Formation of coarse carbides that embrittle the surface layer, microcracks, and spalling due to internal stresses and brittleness. Number B of carbon steels is medium and high carbon steels, more susceptible to carburization because of higher carbon content, increased risk of surface cracking, loss of toughness, and failure under stress. Number 2 of materials affected by carburization damage is alloy steels, includes, number A, low alloy steels, contain alloying elements like chromium, molybdenum, manganese, and nickel in small quantities. These elements can influence carburization behavior. Chromium can form carbides, depleting chromium from the matrix, leading to sensitization. Molybdenum forms stable carbides, which can increase hardness but reduce toughness. Low alloy steels damage, microstructural degradation due to carbide precipitation, loss of corrosion resistance, especially in stainless steels. Number B of alloy steels is high alloy steels such as stainless steels, contain significant amounts of chromium 10.5% and above, and sometimes nickel. While designed for corrosion resistance, they can still be carbidized under aggressive conditions. High alloy steels damage, includes, chromium carbide formation at grain boundaries, causing sensitization, depletion of chromium from the matrix, leading to intergranular corrosion, hard, brittle surface layer prone to cracking and spalling. Number B of alloy steels is high alloy steels such as stainless steels, contain significant amounts of chromium 10.5% and above, and sometimes nickel. While designed for corrosion resistance, they can still be carbidized under aggressive conditions. High alloy steels damage, includes, chromium carbide formation at grain boundaries, causing sensitization, depletion of chromium from the matrix, leading to intergranular corrosion, hard, brittle surface layer prone to cracking and spalling. Number B of cast iron is ductile, nodular, cast iron, spheroidal graphite inclusions within a ductile matrix, susceptible to surface hardening, which can cause cracks around graphite nodules, reduced ductility and toughness at the surface. Number 3 of materials affected by carburization damage is high-temperature alloys. Superalloys, includes, number A, nickel-based superalloys such as Inconel, Hastelloy, used in turbines, heat exchangers, and aerospace components. At high temperatures, they can undergo carburization, leading to formation of carbides that change microstructure, microstructural degradation, such as phase instability. Loss of mechanical strength and corrosion resistance. Number B of high-temperature alloys. Superalloys is stainless steel such as types 304, 316, designed for corrosion resistance, but susceptible to carburization if exposed to carbonizing atmospheres. Stainless steels damage, chromium carbide precipitates at grain boundaries, sensitization, which causes intergranular corrosion and reduced toughness. Number 5 of materials affected by carburization damage is tool steels and special alloys. Let's start from tool steels, composed of high carbon content and alloying elements for hardness and wear resistance, highly susceptible to carburization, which increases surface hardness excessively, causes brittleness and cracking, reduces toughness and tool life. Other special alloys, materials designed for high temperature, high stress environments can still be affected if exposed to carbonizing conditions, leading to microstructural changes and property deterioration. Summary table of carburization damage affected materials. If material type is plain carbon steels, then the specific examples is mild steel, low carbon steel, and then how carburization affects them are surface hardening, embrittlement, cracking. If material type is alloy steels, then the specific examples is CRMO steels, Ni steels, and then how carburization affects them are carbide formation, microstructural degradation, loss of toughness. If material type is cast irons, then the specific examples is gray cast iron, ductile iron, and then how carburization affects them are surface hardening, cracking, spalling. If material type is stainless steels, then the specific examples is 304, 316, 321, and then how carburization affects them are carbide precipitation, sensitization, intergranular corrosion. If material type is superalloys, then the specific examples is Inconel, Hastelloy, and then how carburization affects them are microstructural changes, phase instability, property loss. If material type is tool steels, then the specific examples is D2, H13, and then how carburization affects them are excessive surface hardness, brittleness. In summary, carburization damage affects mainly ferrous materials, particularly steels and cast irons, by increasing surface carbon content, which leads to microstructural changes such as carbide formation, surface hardening, embrittlement, and cracking. These effects compromise mechanical properties, corrosion resistance, and overall component integrity, especially in high-temperature environments. Carburization damage critical factors based on API 571, Number A, 3 conditions must be satisfied. Condition 1, exposure to a carburizing environment or carbonaceous material. Condition 2, temperature high enough to allow diffusion of carbon into the metal, typically above 1100 degrees Fahrenheit or 593 degrees C. And condition 3, susceptible material. Number B, conditions favoring carburization include a high gas phase carbon activity, hydrocarbons, coke, gases rich in CO, CO2, methane, ethane, and low oxygen potential, minimal O2 or steam. Number C, initially, carbon diffuses into the component at a high rate and then tapers off as the depth of carburization increases. Number D, in carbon steels and low alloy steels, carbon reacts to form a hard, brittle structure at the surface that may crack or spall upon cooling. Number E, 300 series SS are more resistant than carbon steel and the low alloy steels due to higher chromium and nickel content. And number F, carburization can result in the loss of high temperature creep ductility, loss of ambient temperature mechanical properties, specifically toughness/ductility, loss of weldability, and corrosion resistance. Certainly. Here's a comprehensive explanation of the critical factors of carburization damage, detailing the key elements that influence the occurrence and severity of carburization-related deterioration. Critical factors of carburization damage. Carburization damage is a complex phenomenon influenced by multiple interrelated factors. Understanding these factors is essential for predicting, preventing, or controlling carburization-related failures in metallic components. Below are the primary critical factors with detailed explanations. Below are the primary critical factors of carburization damage with detailed explanations. Number 1 is temperature of exposure, includes high temperature conditions. Carburization primarily occurs at elevated temperatures, typically between 850 degrees Celsius and 1050 degrees Celsius or 1562 degrees Fahrenheit and 1922 degrees Fahrenheit. The diffusion rate of carbon into steel increases exponentially with temperature. Following Fick's laws, temperatures above certain thresholds accelerate the formation of a thick, brittle carburized layer, increasing risk of microstructural degradation. Temperature gradients, variations in temperature across the component can cause uneven carburization, leading to differential microstructures and residual stresses. Rapid heating or cooling can induce thermal stresses, exacerbating damage. Number 2 of primary critical factors of carburization damage with detailed explanations is duration of exposure, includes time at elevated temperatures. Longer exposure times allow more carbon atoms to diffuse into the material, increasing carburization depth. Prolonged exposure results in a thicker, more brittle case layer, raising the likelihood of cracking, spalling, or embrittlement. Process control. Precise control of process duration is vital to limit carburization to desired depths, especially in heat treatment operations. Number 3 of primary critical factors of carburization damage with detailed explanations is carburizing atmosphere composition includes carbon potential, the presence of carbon-rich gases such as methane, carbon monoxide, or hydrocarbon atmospheres influences the carbon activity. High carbon potential atmospheres promote rapid diffusion and deeper carburization. Atmospheric control, maintaining appropriate atmospheres, e.g., controlled low carbon potentials, can mitigate excessive carburization. Contaminants or impurities in the atmosphere may accelerate unwanted carbon ingress. Number 4 of primary critical factors of carburization damage with detailed explanations is material composition and microstructure, includes alloying elements such as chromium, molybdenum, vanadium, and nickel influence carburization behavior. For example, chromium can form chromium carbides, which can deplete chromium from the matrix and cause sensitization. Microstructural factors, grain size, phase distribution, and prior microstructure affect carbon diffusion rates. Finer grain structures may slow or accelerate carburization depending on the material, initial hardness and surface condition. Hardened or scaled surfaces may either resist or facilitate carbon ingress. Number 5 of primary critical factors of carburization damage with detailed explanations is component geometry and surface area, includes complex geometries, sharp corners, threads, or narrow passages have higher localized carbon flux, leading to uneven carburization. Thinner sections tend to carburize more rapidly than thicker sections. Surface finish. Rough or porous surfaces can trap gases or contaminants, increasing localized carbon potential and diffusion rates. Number 6 of primary critical factors of carburization damage with detailed explanations is presence of residual stresses, pre-existing stresses. Components with residual tensile stresses are more susceptible to crack initiation in the carburized layer. Microcracks can form or propagate under the combined influence of internal stresses and brittleness. Stress concentration, notches, pits, or surface flaws act as stress concentrators, promoting crack initiation during carburization. Number 7 of primary critical factors of carburization damage with detailed explanations is cooling rate post-exposure. Rapid cooling, sudden cooling after carburization can induce thermal stresses due to uneven contraction, leading to cracking. Controlled cooling. Proper cooling rates help relieve residual stresses and minimize damage. Number 7 of primary critical factors of carburization damage with detailed explanations is environmental factors and contaminants. Presence of impurities, sulfur, phosphorus, or other impurities can weaken the microstructure, making it more vulnerable to damage during carburization. Corrosive environments. Corrosion during or after carburization can exacerbate material degradation, especially if the carburized layer becomes porous or cracked. Summary of carburization damage mechanisms. Critical factors. If the factor is temperature, describe as elevated and gradient temperatures, the impact on carburization damage is accelerates carbon diffusion, increases damage risk. If the factor is exposure time, describe as duration at high temperature, the impact on carburization damage is thicker carburized layer, higher embrittlement risk. If the factor is atmosphere composition, describe as carbon potential of gases, the impact on carburization damage is influences rate and depth of carburization. If the factor is material microstructure, describe as alloying elements and grain size, the impact on affects diffusion rate and microstructural stability. If the factor is geometry surface condition, describe as surface irregularities and shape, the impact on carburization damage is causes uneven carburization and localized damage. If the factor is residual stresses, describe as internal stresses pre-existing, the impact on carburization damage is promotes crack initiation and propagation. If the factor is cooling rate, describe as post-exposure cooling process, the impact on carburization damage is affects residual stress development. If the factor is environment contaminants, describe as impurities and corrosive agents, the impact on carburization damage is worsens microstructural degradation. Critical factors. Conclusion. The occurrence and severity of carburization damage depend on a combination of these critical factors. Managing and controlling these variables, through process design, material selection, and operational parameters, are essential strategies to prevent or minimize carburization-related failures in high-temperature components. Carburization damage affected units or equipment based on API 571. Number A. Fired heater tubes are the most common type of equipment susceptible to carburization in the environments mentioned earlier. Number B. Coke deposits are a source of carbon that may promote carburization, particularly during decoke cycles where temperatures exceed the normal operating temperatures, accelerating the carburization. Number C. Carburization is sometimes found in heater tubes in catalytic reformers and coker units or other heaters where steam/air decoking is performed. Number D. Carburization is also encountered in ethylene pyrolysis and steam reformer furnaces. Significant carburization occurs during Deco-King cycles. Certainly. Here's a detailed explanation of the units or equipment affected by carburization damage, focusing on their types, functions, and how carburization impacts their performance and integrity. Affected units and equipment by carburization damage. Carburization damage predominantly affects high-temperature equipment and components used in industries such as power generation, petrochemical processing, aerospace, and manufacturing. These units operate in environments where exposure to carbon-rich atmospheres or gases at elevated temperatures is common, making them susceptible to carburization-related degradation. Affected units and equipment by carburization damage. Number 1 is turbine blades and vanes. Function: critical components in gas turbines and steam turbines responsible for compressing, expanding gases, and converting thermal energy into mechanical work. Turbine blades and vanes. Impact of carburization: surface hardening and embrittlement due to carburization cause cracks, spalling, and ultimately failure. Microcracks can propagate under cyclic thermal and mechanical stresses. Loss of fatigue strength reduces lifespan and increases the risk of sudden failure. Affected units and equipment by carburization damage. Number 2 is heat exchangers and boilers. Function: transfer heat between fluids. Boilers generate steam, and heat exchangers recover heat for energy efficiency. Heat exchangers and boilers. Impact of carburization: carbon diffusion into boiler tubes and heat exchanger shells results in surface embrittlement. Formation of carbides can cause localized corrosion and pitting. Spalled or cracked tubes lead to leaks, reduced efficiency, and potential safety hazards. Affected units and equipment by carburization damage. Number 2 is pressure vessels and reactors. Function: contain high-pressure fluids at elevated temperatures in chemical, petrochemical, and power industries. Pressure vessels and reactors. Impact of carburization: damage to the vessel walls due to surface embrittlement and cracking, degradation of weld zones, which are critical for structural integrity. Increased risk of catastrophic failure if microcracks grow under operational stresses. Affected units and equipment by carburization damage. Number 4 is gas and steam turbine components, rotors, stators. Function: convert high-temperature, high-pressure gases into rotational energy. Gas and steam turbine components. Impact of carburization: surface and subsurface microstructural changes weaken the material. Cracking and spalling reduce aerodynamic efficiency and can cause catastrophic damage. Increased maintenance costs due to frequent inspections and repairs. Affected units and equipment by carburization damage. Number 5 is valves, piping, and fittings. Function: control and direct fluid flow in high-temperature systems. Valves, piping, and fittings. Impact of carburization: surface embrittlement leads to cracking during operation. Carbide precipitates at grain boundaries compromise ductility, reduced lifespan and increased risk of leaks or failure. Affected units and equipment by carburization damage. Number 6 is aero engines and aircraft components. Function: propulsion systems operating at high temperatures and stresses. Aero engines and aircraft components. Impact of carburization: damage to turbine blades, discs, and combustion chambers. Microstructural degradation reduces mechanical strength and fatigue life. Potential for catastrophic failure if not detected and mitigated. Affected units and equipment by carburization damage. Number 7 is high-temperature alloys and chemical processing equipment. Function: used in reactors, furnaces, and other process equipment exposed to aggressive atmospheres. High-temperature alloys and chemical processing equipment. Impact of carburization: carbide formation and surface hardening cause cracking and loss of corrosion resistance. Microstructural instability impacts process safety and efficiency. Affected units and equipment by carburization damage. Number 8 is nuclear reactor components. In some cases, function: core structures, fuel cladding, and other high-temperature components. Nuclear reactor components. Impact of carburization: potential embrittlement and cracking compromise safety, increased risk of failure under operational stresses. Summary table of carburization damage mechanisms. Affected units/equipment. If equipment or unit is turbine blades vanes, then the function is power generation, propulsion, and the carburization effects is surface embrittlement, cracking, spalling. If equipment or unit is heat exchangers boilers, then the function is heat transfer, steam generation, and the carburization effects is tube cracking, corrosion, spalling. If equipment or unit is pressure vessels reactors, then the function is contain high-pressure high-temp fluids, and the carburization effects is microcracks, structural weakening. If equipment or unit is rotors stators, gas steam turbines, then the function is mechanical energy conversion, and the carburization effects is microstructural degradation, cracking. If equipment or unit is valves, piping fittings, then the function is fluid control, and the carburization effects is cracking, embrittlement, reduced lifespan. If the equipment or unit is aero engine components, then its function is propulsion, and then carburization effects would be microstructural damage, reduced fatigue life. If the equipment or unit is chemical processing equipment, then its function is high-temperature chemical reactions, and then carburization effects would be surface hardening, cracking, corrosion. If the equipment or unit is nuclear components, then its function is reactor safety and operation, and then carburization effects would be embrittlement, cracking, safety risks. Carburization damage conclusion. Carburization damage affects a wide range of high-temperature units and equipment, especially those operating in carbonaceous or reducing atmospheres. The damage compromises their structural integrity, mechanical properties, and operational safety, often leading to increased maintenance, reduced service life, and potential catastrophic failure if not properly managed. Preventive measures such as material selection, protective coatings, controlled atmospheres, and regular inspections are crucial to mitigate these effects. The appearance or morphology of carburization damage based on API 571, number A, the depth of carburization can be confirmed by metallography. See Figure 4-121, carburization, dark areas, of an HP-modified tube from an ethylene furnace after 3 years at 1900 degrees Fahrenheit or 1038 degrees Celsius. Number B, see Figure 4-122, a photomicrograph of a cross-section of a 304H cyclone from a fluid coker showing surface carburization after 24 years. Mag. 35X. Number B, carburization can be confirmed by substantial increases in hardness and loss in ductility. Number C, in a more advanced stage, there may be a volumetric increase in the affected component. Number D, a increase, in the level of ferromagnetism can occur in some alloys. And number D, carburization results in the formation of metal carbides depleting the surrounding matrix of the carbide-forming element. Certainly. Here's a detailed explanation of the appearance or morphology of carburization damage, describing how it manifests visually and microstructurally. Appearance and morphology of carburization damage. Carburization damage manifests through distinctive surface and microstructural features that can be observed both macroscopically and microscopically. Understanding these morphologies is crucial for identifying and diagnosing carburization-related problems in high-temperature components. Number 1 of appearance and morphology of carburization damage is macroscopic appearance. The first of it is discoloration and surface changes. The affected surfaces often exhibit discoloration, ranging from dark brown to black, due to oxidation and carbon deposits. The surface may appear rough, pitted, or spalled, especially after microcracking or delamination. In severe cases, spalling or flaking of the surface layer occurs, exposing underlying microstructure. The second of macroscopic appearance is cracks and spalling. Visible cracks, often hairline or macro cracks, can appear on the surface. Spalled fragments may be observed, indicating the failure of the carbized layer due to internal stresses. The third of macroscopic appearance is layered or gradient zones. The surface may show a distinct hardened layer, often visibly different in color or texture, indicating a carbized case. Number 2 of appearance and morphology of carburization damage is microstructural features. The first of it is carbized layer or case. The microstructure within the carbized zone shows significant microstructural transformation compared to the core material, typically consists of a hard, brittle case enriched with carbide phases, such as cementite or Fe3C or complex carbides, which can be observed as fine, needle-like or plate-like precipitates. The second of microstructural features is gradation of composition. There is a gradual transition from the carbized surface to the unaffected core, often with a gradient of carbon concentration. the microstructure transitions from a carbide-rich, hardened layer to the softer, more ductile core. The third of microstructural features is microcracks. Microcracks are prevalent within the carbidized layer, often aligned along grain boundaries or within carbide precipitates. These cracks can be transgranular, through grains, or intergranular, along grain boundaries, depending on the microstructure. The fourth of microstructural features is crack morphology. Cracks are usually fine, hairline, and can originate at surface imperfections or within the carbide network. Under higher magnification, microcracks may appear as networks within the brittle surface layer. The fifth of microstructural features is carbide precipitation. Carbides tend to precipitate along grain boundaries, forming continuous or discontinuous networks. These carbides are often hard, brittle, and can serve as crack initiation sites. The sixth of microstructural features is depletion zones. The microstructure shows depletion of alloying elements like chromium, manganese, or molybdenum near the surface, weakening the matrix. This depletion zone can be observed as a zone with altered microstructure and reduced corrosion resistance, sites. Number 3 of appearance and morphology of carburization damage is morphological indicators of damage. The first of it is cracked and brittle surface. The surface appears cracked, with possible evidence of peeling or spalling. The surface is often roughened and may have microvoids or pits. The second of morphological indicators of damage is presence of microcracks. Microcracks can be observed under microscopy, often aligned along the carbide particles or grain boundaries. These cracks may coalesce and propagate under stress. The third of morphological indicators of damage is microvoids and pits. Microvoids may form due to internal stresses and carbide precipitation. Pitting corrosion can occur at carbide sites, creating localized pits. The fourth of morphological indicators of damage is layer thickness. The carbidized layer can vary from a few micrometers to several millimeters, depending on exposure conditions. The thickness correlates with the severity of carburization and damage. Summary of morphological features. If the feature is discoloration, then its description is dark brown to black surface coloration, and then the significance appearance and morphology of carburization damage indicates oxidation and carbon accumulation. If the feature is cracks, then its description is fine to coarse, micro to macro cracks, and then the significance appearance and morphology of carburization damage is sign of embrittlement and internal stress buildup. If the feature is spalling, then its description is flaking or peeling of the surface layer, and then the significance appearance and morphology of carburization damage is severe damage, exposes underlying microstructure. If the feature is carbide networks, then its description is needle-like or plate-like carbides at grain boundaries, and then the significance appearance and morphology of carburization damage is microstructural hallmark of carburization. If the feature is depletion zones, then its description is reduced alloying elements near surface, and then the significance appearance and morphology of carburization damage is microstructural weakening, increased corrosion risk. If the feature is microvoids and pits, then its description is small voids or pits within the microstructure, and then the significance appearance and morphology of carburization damage is crack initiation sites, corrosion hotspots. Visual aid, conceptual. Imagine a cross-section of a carbidized steel component. The outermost surface appears darker, rough, and cracked. Just beneath the surface, a distinct hardened layer contains numerous carbide particles. Microcracks run within this layer, often originating at carbide interfaces or along grain boundaries. Moving inward, the microstructure gradually returns to the original, more ductile state with fewer carbides and cracks. Conclusion: the morphology of carburization damage is characterized by a hardened, brittle surface layer rich in carbides, often with visible cracks, spalling, and microstructural degradation. These features can be observed macroscopically as surface discoloration, cracks, and spalling, and microscopically as carbide precipitation, microcracks, and depletion zones. Recognizing these morphological indicators is essential for diagnosing carburization damage and implementing appropriate remedial actions. The prevention and mitigation of carburization damage based on API 571, Number A, select alloys with adequate resistance to carburization including alloys with a strong surface oxide or sulfide film formers or silicon and aluminum. Number B, reduce the carbon activity of the environment through lower temperatures and higher oxygen or sulfur partial pressures. Sulfur inhibits carburization and is often added in the process stream in small amounts in steam or gas cracking in olefin and thermal hydrodilkylation units. Certainly. Here's a comprehensive and detailed explanation of prevention and mitigation strategies for carburization damage. Prevention and mitigation of carburization damage. Carburization is a high-temperature process where carbon diffuses into the surface layers of steel or alloy components, leading to microstructural changes such as carbide formation, surface embrittlement, and cracking. Preventing or mitigating this damage requires a combination of material selection, operational controls, protective coatings, and maintenance practices. Number 1 of prevention and mitigation of carburization damage is material selection. Use of low-carbon or carbide-resistant alloys. Select materials with low carbon content or high stability at operating temperatures. Alloys containing elements like chromium, molybdenum, and nickel enhance corrosion resistance and reduce susceptibility to carburization. Examples include stainless steels, e.g., 304, 321, high-nickel alloys, and certain superalloys designed to withstand carbizing. Environments. Alloying elements such as chromium, aluminum, and silicon form stable oxide layers, providing a barrier against carbon ingress. These elements also reduce carbon diffusion rates. Number 2 of prevention and mitigation of carburization damage is protective coatings. Application of surface coatings, ceramic coatings, thermal barrier coatings, e.g., yttriastabilized zirconia, provide a thermal barrier and reduce carbon diffusion. Metallic coatings, overlay coatings such as nickel-based alloys or aluminide coatings act as diffusion barriers. Diffusion coatings, aluminum or chromium diffusion coatings form protective oxide layers that inhibit carbon ingress. Coating techniques, physical vapor deposition or PVD, chemical vapor deposition or CVD, plasma spraying, pack cementation. Number 3 of prevention and mitigation of carburization damage is environmental control. Control of atmosphere, reduce carbon activity in the environment surrounding the component. Use of inert or oxidizing atmospheres such as air, steam, or specific gas mixtures during operation to minimize carbon availability. Avoid reducing atmospheres rich in hydrocarbons or carbonaceous gases unless specifically designed to prevent carburization. Use of gas purification, remove hydrocarbons or carbon-rich gases from the process environment. Employ gas scrubbers and filters to maintain a controlled atmosphere. Number 4 of prevention and mitigation of carburization damage is operational strategies. Includes, the first is temperature control. Operate at the lowest effective temperature to limit carbon diffusion rates. Avoid prolonged exposure to high temperatures that promote carburization. The second of operational strategies is cycle management. Implement controlled heating and cooling cycles to minimize thermal stresses and microcrack formation. Regularly inspect and manage operational parameters to prevent conditions conducive to carburization. The third of operational strategies is fuel and combustion control. Use low-carbon fuels or optimize combustion to reduce the carbon activity in flue gases. Ensure complete combustion to minimize unburned hydrocarbons. Number 4 of prevention and mitigation of carburization damage is design modifications. Includes, the first is component design. Design components with protective barriers or layers to reduce carbon ingress. Use of multi-layered structures with diffusion barriers. The second of design modifications is flow and gas dynamics. Optimize flow paths to minimize carbon-rich gas stagnation zones. Ensure uniform temperature distribution to prevent localized carburization. Number 6 of prevention and mitigation of carburization damage is regular inspection and monitoring. Includes, the first is non-destructive testing or NDT. Employ techniques like ultrasonic testing, eddy current, or radiography to detect early signs of carburization damage. The second of regular inspection and monitoring is microstructural analysis. Regular metallography and microhardness testing to identify carburization zones before critical failure. And the third of regular inspection and monitoring is chemical analysis. Measure carbon content at the surface and subsurface layers periodically. Number 7 of prevention and mitigation of carburization damage is remedial actions and repair. Includes, the first is surface remediation. Remove carbonized layers via grinding or machining. Apply recoating or rehardening processes as needed. The second of remedial actions and repair is material replacement. In severe cases, replace damaged components with carburization-resistant materials. And the third of remedial actions and repair is post-operation heat treatment, carburized. Components can be subjected to heat treatment processes such as annealing to relieve stresses and modify microstructure. Summary of carburization damage prevention and mitigation strategies. If the prevention and mitigation strategies in use is material selection, describe as use low-carbon or alloyed materials resistant to carburization, it is purpose to reduce susceptibility to carbon ingress. If the prevention and mitigation strategies in use is protective coatings, describe as apply ceramic, metallic, or diffusion barrier coatings, it is purpose to physically block carbon diffusion. If the prevention and mitigation strategies in use is environment control, describe as control atmosphere composition and reduce carbon activity, it is purpose to minimize carbon availability in operating environment. If the prevention and mitigation strategies in use is operational control, describe as regulate temperature, cycle time, and combustion conditions, it is purpose to limit diffusion rates and thermal stresses. If the prevention and mitigation strategies in use is design optimization, describe as incorporate diffusion barriers, flow design, and thermal management, it is purpose to prevent localized carburization and hotspots. If the prevention and mitigation strategies in use is inspection monitoring, describe as use NDT and microstructural analysis regularly, it is purpose to detect early signs before failure. If the prevention and mitigation strategies in use is remedial actions, describe as remove or repair carburized layers, replace components, it is purpose to mitigate damage progression and extend lifespan. Conclusion: preventing and mitigating carburization damage involves a multifaceted approach that combines material science, protective technology, operational management, and regular inspection. By understanding the root causes and controlling the environment, temperature, and material properties, industries can significantly extend the service life of high-temperature components and prevent catastrophic failures associated with carburization. Carburization damage inspection and monitoring based on API 571, Number A, inspection for carburization in the initial stages of attack is difficult. If the process side surfaces are accessible, hardness testing and field metallography can be used. Destructive sampling and magnetic-based techniques, eddy current, have also been used. Number B, inspection techniques based on determining increased levels of ferromagnetism, magnetic permeability, are also useful for alloys that are paramagnetic when initially installed, austenitic alloys. However, surface oxides may interfere with the results, and number C, in the advanced stages of carburization where cracking has initiated, RT, UT and some magnetic techniques may be used. Certainly. Here's a detailed overview of inspection and monitoring methods used to detect carburization damage, including their principles, techniques, advantages, and limitations. Inspection and monitoring methods for detecting carburization damage. Detecting carburization early is crucial to prevent catastrophic failure of high-temperature components. Carburization damage primarily affects the microstructure and surface properties, making a combination of non-destructive testing, NDT, microstructural analysis, and chemical testing essential. Inspection and monitoring methods for detecting carburization damage includes: number 1 is visual inspection. Visual inspection principle: basic, initial assessment based on surface appearance. Visual inspection method: examine the component for discoloration, surface cracking, spalling, pitting, or roughness. Use magnifying tools or borescopes for detailed surface examination. Visual inspection advantages: quick, cost-effective, and easy to perform. Visual inspection limitations: cannot detect subsurface or microstructural carburization. Surface defects may be subtle or masked. Number 2 of inspection and monitoring methods for detecting carburization damage is visual and optical microscopy. Principle of visual and optical microscopy is: provides magnified observation of surface microstructure and near-surface features. Method of visual and optical microscopy are: prepare microsections of the component. Use optical microscopes to analyze the microstructure, looking for carbide networks, microcracks, or depletion zones. Advantages of visual and optical microscopy are: direct microstructural information. Can identify microcracks, carbide precipitates, and microvoids. Limitations of visual and optical microscopy requires sample preparation, sectioning, polishing. Destructive or semi-destructive. Number 3 of inspection and monitoring methods for detecting carburization damage is microhardness testing. Principle of microhardness testing is measures hardness variations across the surface and subsurface layers. Method of microhardness testing perform microhardness indentation at various depths. A carburized layer typically shows significantly higher hardness compared to the core. Advantages of microhardness testing quantitative assessment of carburization depth. Sensitive to microstructural changes. Limitations of microhardness testing requires sample extraction. Localized measurement may not represent the whole component. Number 4 of inspection and monitoring methods for detecting carburization damage is non-destructive testing or NDT methods. Number A of NDT method is ultrasonic testing or UT. Principle of UT uses high-frequency sound waves to detect differences in material properties. Method of UT transducers send ultrasonic waves into the material. Changes in wave reflection or transmission indicate microstructural variations. Application of UT detects changes in elastic properties associated with carburized zones. Can identify internal microcracks or voids. Advantages of UT non-invasive. Can be used for thick components. Limitations UT less sensitive to microstructural changes and less significant. Requires skilled operators and calibration. Number B of NDT method is eddy current testing or ECT. Principle of ECT uses electromagnetic induction to detect surface and near-surface defects. Method of ECT eddy currents are affected by changes in conductivity and permeability caused by carburization. Application of ECT suitable for detecting surface or near-surface carburization layers. Advantages of ECT rapid and suitable for in-situ inspection. Sensitive to conductivity changes due to carbide formation. Limitations of ECT limited penetration depth. Less effective on ferromagnetic materials with rough surfaces. Number C of NDT methods is magnetic methods for ferromagnetic materials. Principle of magnetic methods carburization alters magnetic properties. Method of magnetic methods magnetic Barkhausen noise or MBN, and magnetic flux leakage or MFL. Application of magnetic methods detect microstructural changes associated with carburization. Advantages of magnetic methods rapid and non-contact, and limitations of magnetic methods sensitive to surface condition and magnetic saturation. Number 5 of inspection and monitoring methods for detecting carburization damage is chemical and microstructural analysis. Includes, number A, microstructural examination. Use metallography with optical or scanning electron microscopy or SEM to observe carbide networks, depletion zones, and microcracks. Sample preparation involves sectioning, mounting, polishing, and etching. Number B. Chemical analysis. Techniques like energy dispersive X-ray spectroscopy or EDS or wavelength dispersive spectroscopy or WDS can analyze the chemical composition across layers, detects carbon content and alloy element depletion. Advantages of chemical and microstructural analysis definitive microstructural and compositional information. Limitations of chemical and microstructural analysis destructive and time-consuming. Number 6 of inspection and monitoring methods for detecting carburization damage advanced techniques. Number A of advanced techniques is X-ray diffraction or XRD, detects changes in phase composition, such as carbide formation, can identify microstructural stresses induced by carburization. Number B of advanced techniques is laser-induced breakdown spectroscopy or LIBS, rapid surface analysis of elemental composition. Number C of advanced techniques is neutron diffraction. Provides bulk residual stress and phase analysis, useful for thick components. Summary inspection and monitoring methods for detecting carburization damage. If inspection and monitoring methods is visual inspection, then its type is non-invasive, then the key features are surface appearance, discoloration, and then typical use cases are quick screening, initial assessment. If inspection and monitoring methods is microhardness testing, then its type is semi-destructive, then the key features are quantifies carburization depth, and then typical use cases are confirming microstructural changes. If inspection and monitoring methods is optical microscopy, then its type is destructive or semi-destructive, then the key features are microstructure analysis, carbide detection, and then typical use cases are microstructural assessment. If inspection and monitoring methods is ultrasonic testing, then its type is non-invasive, then the key features are internal microcrack detection, and then typical use cases are internal defect detection. If inspection and monitoring methods is eddy current testing, then its type is non-invasive, then the key features are surface or near-surface detection, and then typical use cases are rapid inspection of surface areas. If inspection and monitoring methods is magnetic methods, then its type is non-invasive, then the key features are magnetic property changes, and then typical use cases are ferromagnetic components. If inspection and monitoring methods is chemical microstructural analysis, then its type is destructive, then the key features are composition and phase identification, and then typical use cases are confirmatory diagnosis. If inspection and monitoring methods is X-ray diffraction, then its type is non-invasive or microdestructive, then the key features are phase analysis, stress measurement, and then typical use cases are microstructural diagnostics. Monitoring strategies, regular inspections, schedule periodic visual, ultrasonic, or eddy current inspections during maintenance, trend analysis, track changes over time to identify early signs of carburization, sampling, extract microsections periodically for microstructural and chemical analysis to verify the extent of carburization. Carburization damage inspection and monitoring conclusion. Detecting carburization damage involves a combination of visual, microstructural, chemical, and non-destructive testing methods. The choice of method depends on the component size, accessibility, required sensitivity, and whether destructive testing is permissible. Early detection through these methods enables timely maintenance and prevents catastrophic failures. Thank you.